Welcome to the German Center on Quantum Computing. This time we have Kristian, Wold, and Sølve Selstø from OsloMet, and they're going to talk about what goes on at the OsloMet Quantum Hub.
Thank you. So thanks for the invitation. It's very nice for me to be back in, I think it was like 15 years ago, I was a postdoc here at what was called the Center for Mathematical Applications. And that's where I met Hans, which was a happy meeting. I'm thrilled to be back to see you on the building again. I would like to start, I would like to talk about some quantum computing and quantum technology applications and projects we're doing, but I would like to start with some disclaimers. You already explained one of them, just to say, that it's not just me lecturing. What happened there? I seem to have clicked something stupid. But anyway, can you still see what you're supposed to see on the screen, or do you see the web browser? Looks good. Yeah, here it looks good, but on Zoom.
They should
I guess anyone with I hope so. Yeah. So it's not just me, it's also Kristian. Instead of me trying to give my interpretation of what he's doing as a prolific PhD, he should explain that himself. So that's something to look forward to towards the end. I just want to say a little bit about who we are. So at the OsloMet Quantum University, we don't have, it's not a traditional university, really. It's more about professional education for vocations. It doesn't have this sort of physics department or a mathematics department. It has physicists and mathematics and sort of scattered group of students and colleagues. So in this context, I think quantum computing, we thought, my colleague Simon Breck a few years ago suggested that quantum computing, quantum information technology could be a nice way to bring people together because it overlaps with so many fields, right? So we did that, and it seems to work. Just to illustrate, it's a bit of a mess of different headings, so to speak, in the topics and the roles of different. Of course, there are multiple arrows and many other people. I think it's a nice mess. It serves to bring people together. First disclaimer, when I say that it's the OsloMet Quantum Hub, it's because there are many quantum hubs around, and this is the OsloMet, so it's just to disambiguate. It's not because we want it to be exclusive by any means, of course. Secondly, it's not just about research and development. Actually, it's not even primarily about that, at least according to our application when we got internal funding for this project. Seriously, I think it's fair to say that education is the most important part of it. We want to take IT professionals, computer science students primarily, and make them quantum literate to prepare them for a job market where I think knowing a little bit of quantum technology and quantum computing will add constructively to the CV. So we dedicate ourselves quite a bit to that. In this regard, there's this question which you probably have discussed with colleagues already, whether you really need to know anything about quantum computing quantum physics to do quantum computing. We, together with a colleague, Berit Dungum at NTNU, we sort of tried to survey this a little bit, talk with the students, interview them. And, of course, these are students who know a little bit of mathematics, but, well, not much, but even less about physics, really, and definitely nothing about quantum physics. So should we confuse them with that, or should we just let them do their matrix products and tensor products and stuff like that, and treat it sort of mathematically? One of the answers we got from one of the students was, I think this is quite representative, because we do actually introduce them a little bit superficially by computational means to quantum physics, trying to learn the phenomenology a little bit. And one of the students in an interview would answer, learning about the physics behind makes it easier to swallow all these ideas that quantum computing is using to do calculations and all the algorithms we're looking at. So that's music in my ears. I agree with this. Not all of my colleagues do, but of course there is a risk that this is an echo of what one of his lecturers has implicitly, not explicitly told him, but I think it's fair to know where this strangeness comes from. That's one aspect of it. Another aspect of it is more wide, and maybe I'm stretching it a bit now, but I think this quote from William Hurley is illustrative. My point is, if you sort of expand your mind and see that the world is actually strange when you look at the micro world, you may be able to think less classically about problem solving in general. I think the quote is, I think you're all focused on the wrong problem in quantum computing. I think people are thinking too classically, trying to solve classical problems with quantum computing. I do not care about better drug design. I care about eradicating disease. I am not focused on applying quantum on the problems of today. I'm focused on the trillions of dollars of opportunity and world-changing capabilities that these machines can bring to bear. I encourage all my customers to focus on the sci-fi things that they're dreaming of. That is literally what these machines are for. It's a bit extreme, but I kind of like it. Anyway, so education is one of the things we're dedicated to it. Another one falls very much in line with your ambitions, obviously, right? With outreach and making the public aware of this emerging technology. Maybe it's premature to call it emerging. I guess that was the message from one of our invitees on Tuesday, I think, but I still like that word. It will emerge at some point. And people should know about it. And of course, I'm thrilled to I try to illustrate this common interest by having both of you from this very interesting talk you gave at the Techno talks you gave at Techno in this regard. So I'm happy that we're pulling together this. It's not so easy to see that it's you. It's kind of small, but it's you. It's you. I think doing things together like this event we had on Monday and Tuesday is what we need to do, and we need to do more of that, and we need to do it together, obviously, right? So that's a little bit about what we are aiming for, and it's the Quantum Hub. It's not called the Quantum Computing Hub. It's not quantum computing only. In this regard, we're very happy to bring on board Andrea Stadius, who's doing quantum chemistry. I think many of you know him, and we're thrilled with everything he brings on board, and that includes obviously a strong connection to the University of Oslo, which is a connection which can definitely be strong. Personally, my background is not in quantum computing at all. It's about attosecond physics, particularly looking at magnetic and relativistic effects of photoionization. I think open quantum system is an important topic in our group, common interest of Sølve, illustrated with the Lindblad equation here. And also, at least for me, non-Hermitian quantum physics is also an interesting topic, which again falls very nice together with the Lindblad equation. For instance, when you try and understand measurement, try to model technically measurement in quantum physics. This is how, I mean, if you have this traditional double slit experiment and you measure, eat, and count whatever you eat at the range which is very close to the double slit, of course, you distort a lot of it if it doesn't have time to interfere before you eat it. Right? So that's what I try to illustrate here with how the interference pattern is affected by where you put your absorber. So it converges, of course. The traditional result is it is far away, which it typically is. Anyway, so that's a little bit of context. So but I guess you're here to hear about quantum computing. So let's do that. I think it's fair to say that our main directions is twofold. Of course, this crossroad is not a good illustration because these topics definitely overlap, contrary to roads. But I think considering noise intermediate scale quantum computers as open system is a general topic of our interest. I mean, from a physics point of view, it's like an openness lab, right? We can study them and we can learn something about the physics of openness and mathematics of openness in doing that. We can also, and hopefully learning about these things will also make us able to mitigate error in a better way. Kristian will tell us how later on. And I think quantum machine learning is definitely also an overlap in interest with, for instance, the AI environment and the Nostar group at OsloMet. And of course, these two topics are not mutually exclusive. In the relation to the first one, it's worth mentioning that one of our colleagues, Sergei Denisov, is a principal investigator of a Quantera funded project called DQuant, which is exactly about studying openness in noise intermediate scale quantum computers, disk computers. Not just to sort of try and fight it. I mean, the NISC world is a room or a house we're confined to for quite some time. So we might as well get used to it, right? And start seeing how we can mitigate that in a good way, but also how we can even harness it, exploit it. For instance, you can use steady states of open, of master equations, of steady states of naturally open systems to actually preserve entanglement. It's not necessarily the enemy always. So this project goes along those lines, together with colleagues in other European countries. So this is sort of a try to summarize the main directions and the main projects that we're dealing with. We will get into some detail, not much, most of them, except this one, because it's not really started. We're hiring these days. It's about developing and testing numerical methods for evolving. My background is in explicitly time-dependent systems, so I want to keep on doing that, dealing with evolving in time matrices in quantum physics. Typically density matrices, could be other things as well, but obviously this has applications also in this computing. And personally, I would like to see if we can do something fun when it comes to analog computing, not digital computing, annealing, adiabatic quantum computing, those kind of things. That's in the forge. So I will not say more about that. I will say a little bit about this project that I guess many of you were there online, at least on Tuesday, right? Listening to Maya? No?
I couldn't join.
Ah, I know you were at least. So I won't say so much about it. I couldn't anyway, because I don't know that much about it, but it's very much the other end of the stack from where I'm sort of at the bottom of the stack here, but this is really at the top of it. Just press play, use it. And there's something really appealing about it, because seemingly naive. I mean, Umayyad himself is not really an expert on quantum computing, but just let's try and see. I like that attitude, and it's definitely the most close to the real world applications of quantum computing I've seen, and it actually indicates a potential advantage already. I think that's interesting. Just running an established, more or less established algorithm on a D-web annealer. Of course, when I say 5,000 qubits, that's definitely not logical ones, obviously, but it's still something. And I think his results are quite interesting. And he's doing this in comparison with people at Arberg. He's working at Ruta. I think that was pretty clear from it.
Sorry, can you give me a bit more details of this?
No, I don't. Sorry. But please try. I don't know too much detail on it.
Okay.
I mean, but please try and ask if you have specific questions. I can try.
Yeah, because people in my field are very skeptical of these D-wave devices. So usually it's not clear.
No, I know that they're striving to prove an actual quantum advantage on this, and it's not. I know that it's not. It's not. There's not a definite answer, and this project does not provide a definite answer either.
So what
it
was
does provide a
what was the result?
Sorry.
What was the result of the project?
The result was a slight enhancement of predictability compared to classical AI algorithms in terms of number of passengers predictions.
Okay, classical algorithm that Router uses, or that okay.
So of course, I'm not saying that the classical algorithm does not have room for improvement either. So this is not a proof, but it's interesting. That's what I'm saying.
Yeah. So they actually have a D-wave.
No, it's a cloud access via Amazon Bracket, I suppose. So that we have not bought a D-wave. We have 2 and 3 qubits, not 5,000. not that much money. But it's nice to have this cloud possibilities. Another project, which I also do not know too much details about, is the PhD project of Heino Olga, who is also doing AI and possibly quantum. We hope that we can see, at least get an answer of whether it looks promising quantum-wise. But it definitely involves machine learning. So it's about trying to find methods and strategies for personalizing cancer treatments. This is collaboration with University of Oslo and Oslo University Hospital and Nostad, so it's a bit of a joint venture. So there's a lot of data on cancer patients, and you try this and you try that, and doctors tend to do that based on their own judgment. The human learning, maybe machines can do better, and maybe quantum machines can do even better than that. So it's not necessarily something that will revolutionize it, but it's worth seeing if there's could be a quantum advantage.
Is there any evidence for this?
I'm tempted to say no, but then again, I don't know too much about it. I think my understanding of it is it's pretty much the same attitude as I mentioned before. Let's try and see.
Okay.
So we have not promised groundbreaking deliveries on this one, but we want to try. They want to try. I'm not directly involved in this. There is reason to believe that machine learning at least will provide improvement.
And again, what is he using? What kind of, is it again called?
I think it's pretty much the same machinery as this QVist thing, probably. And then what else? This is a fun project. Again, I should be careful to promise details because I'm not involved in this one either. It's a master project which is about trying to learn a quantum circuit to behave as a cell of automata, both deterministic and stochastic ones, trying to reproduce well-known rules using a pretty, well, a universal, but a pretty shallow, I believe, circuit of quantum computing and see if it can behave the same way. I believe they're using, do you know, is it reinforcement learning to try and mimic it? Or
it's like evolutionary programming.
Right.
They evolve these
right.
With generations and mutations.
Yes, and mimicking what happen in a classical cellular automata.
Yes, yes.
And of course, the stochasticness would emerge from measurements in this context. So it's fun to play with, not something that will save the world, I think, today, but nice little master thesis, I think. I think I will hand over to you.
Yes. Thank you. So I could just make a real quick introduction of myself. I'm Kristian, and I come from UIO originally. So this is a place I know very well. So it's very dear to me. And I got a bachelor's in physics, and then I continued doing basically computational physics. And now I am a PhD candidate at OsloMet, doing mainly research on open quantum systems, quite a bit of machine learning, and it is in the context of these NISQ computers. So my work is sort of like interdisciplinary. There is a lot of numerics, a lot of programming. We also do a lot of experiments using these IBM cloud platforms to gather data. And there are also quite some theoretical aspects, such as how to formulate these quantum maps in the best possible way. So I don't have very much time, and there's very much I want to say. So let's just jump right into it. I will give you a rundown on some projects which I'm directly involved with, either as a supervisor, co-supervisor, or my own project. So the first project reads constructing quantum gates using optimization techniques. And this is the project of Didrik Oksnes. And so what really is it that we are optimizing? We are optimizing parameters of a physically motivated model. More specifically, we are optimizing the parameters of this sort of Hamiltonian. The Hamiltonian, of course, is this mathematical object which encodes all the details of some quantum system. And to be even more specific, this particular Hamiltonian basically models this spin system. We have two spins which are close to each other, and they are these two-level quantum systems. And this can potentially, this is all theoretical, but this can be realized in a laboratory as a crystal perhaps. And this first term here in the Hamiltonian is a time-dependent external magnetic field. This can be something that you apply to your crystal in some way. And the last term is an interacting term between the spins. So this could perhaps result from some material property, or you can perhaps tune this by changing the distance between the spins. Anyway, so this is basically our model of this thing. And since the Hamiltonian encodes all the information about the system, it also dictates how the system evolves in time. So we basically can find out by solving the Schrödinger equation, to find what dynamical action does this actually implement on these two spins. So this basically realizes a quantum gate. So this can be thought of as a quantum computation by letting this Hamiltonian act on your system. Let's say it's in a starting state psi1, and after doing this evolution, you end up in psi2. So now you have sort of like done computation in a very simple sense on this 2-qubit system. So this is a quantum gate, and the quantum gate is defined by the parameters. So what is it that we actually want to do? Let's say we want to realize one specific quantum gate. What we can do is basically, let's say we have some target unitary that we want to attain. Then the question is, can we actually reach this by this parametric form of the Hamiltonian? Can we change these parameters such that we implement some kind of gate that we want? And we can basically formulate a cost function. This is sort of building on the framework of machine learning. We can define some distance measure between the target that we want and our parametric form. And then we can basically do gradient descent. We can calculate the gradient of this cost function, usually by just a finite difference scheme. So this, we basically have to iterate, and we need to solve the Schrödinger equation multiple times in order to establish this gradient. And then we need to do gradient steps over and over again. And hopefully we will reach some kind of local minima. So this is an example of how the loss landscape looks like for a specific parameterization and for a specific target. I don't exactly remember which target. Probably Harmar. Yes, so that will be a 1-qubit. Yes, we also have done.
I think this was 1-qubit.
Yes, fair enough. Yes, as you can see, the landscape is quite non-convex with many local minima. So we often get stuck in very suboptimal solutions, but we have been able to remedy this by doing more like sophisticated ways of doing optimization. We start multiple places in the landscape and do like the momentum gradient descent. And the way forward we can perhaps elevate this thing to not being just a ideal sort of system, but we can add this with the terms. And when we then do optimizations, maybe we can recover these ideal things, not completely, but maybe we can reach them to some useful fidelity, even in the presence of noise. Okay, so the next project reads neural quantum states with restricted Boltzmann machines. And this is the project of Sebastian. So what is known is that generally large quantum systems are in general intractable to simulate. And this comes from the fact that you need an exponential amount of information to represent large quantum systems. But luckily, physically relevant systems are not completely general. Very often, physical systems has a lot of structure in them. For example, we are investigating these Ising type of models where you have these spins in maybe some sort of crystal. And the sort of dynamics which describes this is mainly dominated by pairwise interactions and also very local interactions. These are very like big constraints on the system. And what this usually leads to is that many of the amplitudes are very close to zero. So by storing these amplitudes explicitly in a classical computer would be a very naive way indeed, because many of them are very close to zero, or not necessarily close to zero, but they have some structure to them. So whereas there's structure, there is opportunity to compress information. A very nice analogy is, for example, take an image. A typical full HD image has a 2 million pixel values, but a lot of them are like photographs of real life things are not like very arbitrary information. Many of the pixels have the same values, And so there are opportunities to compress. So we try to compress this information of the quantum state by using basically a neural representation of the wave function. So we learn a compressed function. In this case, using a restricted Boltzmann machine, which is a type of neural network. And basically, we get this huge advantage that the number of degrees of freedom or parameters of the neural network is a lot lower than the explicit amplitudes, which actually describe this physical system. But this only works if there is structure present, which we can abuse. But there often is in these chemical problems and material science problems, there is a lot of structure to the thing. So we can often use, so by having this parametric form, this Boltzmann machine, it lets us do things like Monte Carlo sampling to estimate interesting properties of the system. And as you can see, during sampling, the Monte Carlo approach has a big edge because, as you see, a lot of the amplitudes are indeed very close to zero. The physically relevant states are extremely localized to some few configurations. So this is potentially a very nice approach for tackling very large physically relevant quantum systems.
So how does this compare to other methods like PEPs? If you now compare this to do you know this projected entangled pair states?
Right. It's a very good question. So it's a very good question, and it's an important question. I don't have these details as of now, I would say.
Have you compared this for
not yet.
The ground states?
No, not yet.
Okay.
We are still in the stages of building this up, really. Okay. So this is a very early result. This is not even a quantum system that it has learned. This is just the basically we're doing sampling from the untrained Boltzmann machine. So this is what you basically get when you just initialize the parameters to random values. It is something that is very localized, it turns out. So you could reverse engineer it and say a random Boltzmann machine creates some kind of physical system. But yeah.
Could you combine this with PEPs? In your way that you learn the parameters of the...
Yeah, for sure. There are. So this is a very pure machine learning approach. This is basically we encode the wave function itself as a neural network. But of course, you can try to learn with the help of machine learning. With your approach, you basically have a lot of structure from before, and then you use machine learning to bring it home, so to speak. It's you can do Harvard methods as well. Okay, so deep quantum Q learning, and this is the project of Matthias, and this has not started yet, but it will start next spring. And here we will attempt to basically use quantum machine learning in the context of reinforcement learning. So this is basically utilizing a quantum computer in order to implement quantum algorithms which do machine learning. And we will do so in the context of reinforcement learning, which is basically this methodology where you have this agent which interacts with some kind of environment. And then the agent needs to discover policies from the feedback of this environment and find the optimal way of doing things such that its reward, which is the feedback signal, gets maximized. And this is generally a very hard problem because the reward is a extremely, you could say, sparse signal in the sense that it's only a scalar value. The agent gets a large scalar value when it's doing good, and it gets a low one when it's doing bad. So it doesn't get any information what it did wrong, only that it did something wrong. So just using this sparse feedback, the goal is to basically discover the correct policies which optimize this reward. And like classically, if you have heard of things like AlphaGo, from DeepMind, which has basically solved the game of Go. The working horse of reinforcement learning these days are classical neural networks. So basically, the neural networks gets, after training, it gets fed some state vector, which represent the environment, and it outputs what is the best possible action. So what we want to do is we want to simply switch out this neural network with something which can be called a quantum neural network. So this is a quantum algorithm where the gates are actually dependent on data and parameters. So the first typical gates are dependent on the parameters or the features that are extracted from the environment. Then we do a lot of parametric quantum gates, which are indeed dependent on parameters. These needs to be optimized. And finally, we do some measurement on the quantum circuit, and the measurement outcomes dictate what action should the agent take next. So this is a yes, this is a short thesis, so we don't have time to basically build all of these things up from ground up. So instead, we're going to use much more high-level frameworks, which there have been a lot of advantage, or lately there's been a huge surge in development in these big frameworks, so that they actually incorporate quantum machine learning. So we will use the very famous TensorFlow framework for implementing all sorts of general machine learning models. And then we will use the penny lane backend, which integrates with TensorFlow, which lets you simulate these quantum circuits, both on classical machines and on real hardware. So how's my time doing? It's getting late.
4:15.
Okay. All right. So some of the things that we have to do is to contrast the performance of these quantum solutions to classical problems. So this is not a new methodology to use quantum machine learning for reinforcement learning, but there are still a lot of untried benchmarks. The benchmarks that have been tried so far are very simple. So we want to see if we scale up these to harder problems, how do actually classical solutions and quantum solutions actually compare.
Sorry, can I ask a clarification? So you want to do like classical machine learning on a quantum computer? Is this what you're doing?
No, it's not a one-to-one relation.
No, sorry.
A classical
You want to solve a classical problem.
It's indeed a classical problem.
Okay.
So we can keep the sort of reinforcement learning pipeline very much as it is. It's sort of a Lego set in the sense that you take this Lego piece, which is the classical neural network, rip it out, you stick in what is known as a quantum neural network, and then you see how it goes.
Yes. In some sense, that's the same thing as Heine and Meyer is doing.
Right.
It's a classical problem with a classical solution, but maybe some quantum in between, right?
Yes, exactly. Yes.
Yeah, can you explain why it should be good to have a quantum circuit instead?
So that's very hard to explain because it's a very heuristic method. And basically along the same lines that the Sølve already talked, it is very heuristic indeed. It's very trial and error in spirit. It's basically, we throw quantum machine learning at it and see what happens. Because this is indeed a classical problem. And like with classical information, it's really hard to have any like sort of, what's it called? It's hard to really expect speed ups. You just have to try it, basically. So,
then again, I think speed up or efficiency in classical machine learning is not that obvious either.
Right.
So I think it's fair to say it's worth a try, isn't it?
Yeah. So machine learning is by nature very like heuristic indeed. So this is the engineering way. Just try it. Yes. Okay. So last is my project, which is modeling noisy intermediate scale quantum computers as open quantum systems. So what we essentially want to do is we have this, for example, some sort of real quantum hardware, and we wanted to implement some kind of unitary operation, some kind of quantum circuit. But as we know, because of noise present in the machinery, it doesn't actually implement the unitary description or the circuit description that we wanted to. And this is because of noise. So how can we retrieve an accurate model of today's noisy quantum computers? And basically what we do is this very broad methodology, which is called quantum process tomography, where we basically try to retrieve information about this quantum hardware for a specific circuit descriptions from these input-output pairs. So we basically probe the hardware with a lot of different inputs, see what comes out, and try to reconstruct what's happening in the black box, so to speak. So these Xi's and Yi's are the input states that we throw at the quantum computer. We are generally using IBM quantum platform these days. And then we measure some outputs, usually polystrings, but yeah, we can go into details later. And what we can basically do is we can make a parametric model of a quantum computer. We can basically make a digital twin as a parametric form of a quantum map or quantum channel in general. So we can look at this as a sort of digital twin of this real hardware. So what we can basically do is we can replicate the input-output pairs on the digital twin. And before we adjust these parameters, there's no reason to believe that these output pairs should match, but that's what we want to achieve. So again, we can introduce some kind of cost function, which basically measures the distance between the outputs retrieved from the real hardware and the outputs retrieved from the digital twin. And the sort of goal then would be to optimize this parameter such that these output pairs match sort of, yeah. So this is basically, there's a lot of details I'm skipping now, of course, but this is a very general approach for this retrieving a description of a quantum computer, a quite general description of quantum computer. And what we basically can do from this mathematical model is that we can retrieve a lot of interesting properties. For example, we can compute the spectrum of the quantum map, which represents the quantum computer, which I will talk about shortly. We can also retrieve things as asymptotic states. What do we get when we let the quantum computer run for a very long time? We can also estimate sort of a notion of effective rank. How complicated are the noise effects that are present in the quantum hardware? And this is a very new data that we have gotten actually. This is the spectrum of a quantum computer, of the map of it, approximating a quantum computer, and the different colors are the same circuit, but we introduce a time delay after the circuit before we do the final measurement in order to sort of artificially introduce more noise to the computer. So we get a very characteristic property that these spectra, they start out as rings when the quantum computer is in a sort of ideal, not ideal, but when you have minimal noise, the spectrum starts out being very, very ring-like and close to the unit circle. It's sort of close to being unitary. But as you introduce more noise, you see that we get this collapse of the ring and broadening of the ring. And at some point, we get a transition where the ring collapses into a disk. And this is what we see also from theoretical models, more like sort of toy models, where you can adjust the amount of dissipation in these things. These are completely theoretical results, where we see this collapse, and we see that we also have this for actual real quantum computing. So we have this sort of qualitative result that they are corresponding. Yes, so this is basically plotting the outer and inner radius as a function of delay, and you can see that the inner radius goes towards 0. Yeah, so
this is an actual IBM device.
Yeah.
That is. Okay.
Yes, it's a quite small one. It's a 5-qubit system, but we are only retrieving the map for 3 qubits, which doesn't sound like a lot, but for 3 qubits you already have like 1,000 free parameters to tune in your description of the quantum computer. And really the bottleneck is that we need to probe it with a very large number of inputs in order to sort of like get the full story of what's happening inside.
Why do you have 1,000 free parameters?
It's a full, yes. So this would be a full rank Krauss map for 3 qubits. So that would be 1,024 parameters or something.
Right.
64 times 64. Oh, 32 times 32, yes. Yes?
Yeah, I can.
Do you have, do you have any idea for how to scale this up?
Yes. So in order to scale this up, if the goal is to sort of like do as many qubits as possible, what you basically have to do is you have to assume a lot of structure. So we have basically gone the opposite way with this framework, at least in the beginning, that we want to retrieve as general formulation as possible. So we fit the possibly most general model to the data. In order to scale this, you can't really do that because you will have like some million parameters. I think the most we can hope to actually retrieve on like classical computers are like for, I think 7 or 8 qubits is the absolute max. Then you are really pushing how much RAM you have. So you basically have to make a much more sparser model. You have to make a formulation which abuses sort of like local effects rather than global effects. But then the never-ending question is, are you in a good position to assume this locality? Why should the actual quantum computers have this structure? So yeah, we were starting in the other end.
Yes.
Let's be as general as possible.
I think if you have the sparse Pauli Lindblad models, then you look at the topology of the qubits, and then you take only the local interactions. Exactly. And you assume that far away qubits are negligible have negligible interactions.
Yes. And by all means, that is often surely a good assumption. Yes, indeed. So this is basically how far can we get without those assumptions. Just yeah. All right. Yeah, the work was one of like, so this is a very diagnostic approach. It's about understanding the sickness of quantum computing, which is noise. Some people think it's a sickness. Maybe it could be also, as Sølve said, dissipation could be a resource, of course. We know that dissipation of quantum computers are extremely interesting. It's at least intractable to simulate these 50 qubits in these computers, even though what they produce is not necessarily usable. It is indeed hard, so there is something mathematically very strong going on. Maybe it can be used as a resource, but yeah, we're trying to understand the signatures of these things first, and then the goal down the line will be to cure the sickness, either in doing some fancy quantum error mitigation. We will soon be in a position to really tailor these techniques for specific hardware, where we basically do a very thorough diagnostics on some hardware, and then we deploy some kind of error mitigation, which try to abuse these specific characteristics of the quantum computer, or repurpose them as a resource. Yes.
Okay, let's thank the speakers again.